All right, we will continue with these examples a little bit more, and then I'll teach a specialized simplex algorithm for MCNFP problem. But before I go on, any questions from the assignment representation as MCNFP? Okay, then another example. Okay, single pair shortest path problem. Okay, I'll first explain you what the problem is, and then we're going to formulate this problem as an MCNFP problem. Okay, so we have a graph. All right, some sort, directions. We have a directed graph with nodes and arcs. Okay, and there is a cost of using the arc for each arc, Cij. Okay, there are two specialized vertices that we call S and T, because the problem is actually defined on these S and T. So the problem is, then find me the shortest path from S to T. All right, shortest path, shortest distance. Yeah, this is what actually Google Maps keeps doing when you give them a source and a sink, and then the algorithm works and finds your shortest path, right? So that is our problem now, over a directed graph with directions, because usually highways are also one way or two way, whatever. So the problem is, find the path from S to T with minimum total cost. Okay. Now we will represent this problem. We will formulate this problem as an MCNFP. The network is already there, right? All you're supposed to do is come up with B values, U values, and Cij values. Now, since the answer is already there, it's not easy for me to ask questions, but let's look at this graph. It says, find me a shortest path from S to T. Now, this is an easier version. By just looking at it, you can find the shortest path, right? You have to start from S, and you have to reach T. So going out from S, I guess this is the shortest path. The link, the total cost is 6. Yeah, I think it's here. Yeah, the total cost is 6, and the shortest path from S to T is S to 5T. Okay. Now, how can we formulate this as an MCNFP and give it to our solvers and get an optimum solution easily? Yeah. Let's recall the methodology. We're going to form the network. We're going to come up with our parameters BCU, and then we're going to observe that if I solve MCNFP over this network I just created, I will be actually solving a shortest path problem from S to T, because that's what I actually started. Yeah? Okay. Form the network. Well, the network is already given this time. I don't need to do anything. There is a network from S to T, and the costs are already there. So Cij is also, again, immediate. I need to find my B's and my U's. Now, B is how much supply each node has and how much demand each node has. Now, when you think about it, I'm trying to find a path from S to T with minimum total cost. So if I send 1 unit from S, and if T requires 1 unit, then actually I'll try to set, my network will, my MCNFP formulation will dispatch 1 unit from S and absorb 1 unit in T. That's what I want. So if I will assign this guy as a +1 and this guy as a -1, and everybody else gets a 0. Yeah? Then that means S is sending 1 and T is requiring 6. Oh, the example was 1 to 6, sorry. So it's usually source and sink, but so 1 is sending 1 unit and 6 is absorbing 1 unit. Okay? So B's are fine. C's as given. U, the upper bound on the arcs. Well, I'm trying to find the path. I'm only sending 1 unit. So Uij equals 1 will work. If I use the arc, I will only send 1 unit anyway. I won't send 10 units. It doesn't make sense. I'm just trying to find the path. Yeah. So with this definition, then from 1, I'll have 1 unit out. From 6, I'll have 1 unit in. And everybody else will say out minus n equals to 0. And xij is the amount of flow over that arc, right? That will solve me the MCNFP formulation. Let me write the formulation here. So I'm going to minimize Cij, Xij, subject to Xij minus Xji out minus n equals Bi for all I, right? And I will have Xij between zeros and ones. Now, for this specific problem, then, this formulation, if I is 1, this constraint will say summation x1j minus summation xj1 will be equal to plus 1. Now, look at my network. There is no arc with j1. I can't have this, right? So this will immediately say from node 1, dispatch 1 unit. Okay. When I equals to 6, this formulation will say there is no arc out from 6 anyway. Out x6j minus xj6 equals minus 1. Yeah. So this is not. So there will be 1 arc coming to j6. And for I in between, let me write it here with a different color. For I 2 to 5, it will say x, let's say for 2, 2j minus j2 equals to 0. Anybody into 2 will be out. Anybody into 3 will be out. So you will write 5 of these. So at the end, you will write 6 constraints for your flow balance. And when you solve your formulation, your axis will be like, since this is the minimum cost, it will select these arcs. When you look at it from 1, there is 1 arc going out. For 2, 1 out, 1 in, balance is 0. For 5, 1 out, 1 in, balance is again 0. And for 6, there is 1, so the summation in is minus 1. S and T is 1 and 6. I begin with S and T, sorry, because it's the general version. In this example, it's 1 and 6. S is 1, T is 6. Any other questions, or is it clear? So as you see, this version, the network was already there with the costs, okay? You just need to come up with B values and U values correctly, so that when I solve MCNFP, I'll actually get the shortest path from S to T, from 1 to 6. All right? Any questions on this? Again, it's important to start thinking with this mindset, with the B values, with the upper bounds, all right? Because if you can put correct Bs, then converting the problems to networks is not that problematic, is not that big challenge, right? Another example, max flow. All right, so let's look at the problem from a normal integer programming perspective first, and then we're going to convert it to MCNFP. Maximum flow. This is also, again, a valid network flow problem that you may be encountering. So you have a directed graph again, and you specify 2 distinct nodes, S and T again. That happened to be 1 and 6 at the previous example, but now this is it. This time, I don't care about cost. I don't know what the cost is, but I don't care. All I'm thinking about is, what is the largest amount I can send from S to T? This is a special problem. It's called maximum flow problem. What is the largest amount you can send from S to T? But then you got to have capacities, right? If there is no capacities on my arcs, then the output of this problem is unbounded, infinity, which doesn't make sense. If this problem is valid, that means it's over the capacitated network, and you're trying to find out what is the largest amount you can send between two specific nodes. We name them as S and T. All right. From integer programming perspective, the formulation is as it's written in here. What do we want? We want to send the largest amount from S to T. Yeah. So we name it as V. Okay. So from S, I will be sending V units. And that V units should arrive to node T. And anybody in between should just send it, right? If it receives, it should send, because I don't care about them. And my flow should satisfy the bounds on the arc. So what is the largest amount I could send is the question. Okay, maximizing V, subject to from S, dispatch V units. Well, T should also absorb V units, and everybody else should have out minus N equals to 0. Flow balance. Well, this part definitely looks my flow balance, but then the objective is maximizing V. How do we convert this to MCNFP? Because the constraint structure is very similar, right? We have flow balance, some sort of, yeah, and the upper bounds. These are all fine. I don't have costs, and the objective is maximizing V, which has nothing to do with my MCNFP. So how can I convert this so that in the converted model, I solve MCNFP, and at the end, I actually find the maximum flow from S to T. This is a little challenging than shortest path or assignment, right? Because the objective is different. And there are no costs in the original formulation. I need to come up with those this time. Let's see how it works. Okay. The same example in a largened version. This time again, S will be 1, T is 8. Yeah, I will represent them. So, okay. First of all, I have to convert this max objective to mean cost objective, right? And then we don't know the V, which is the objective in here, and which is also in the flow balance. Yeah. But I need a value for that. Because if I were to convert this to MCNFP, I can't have a variable in the right-hand side. I have to have B's there, the demands and supplies, right? So how do I do this? I have to make sure that this thing is as large as possible from S to T. Now, here's the trick that we're going to do. We're going to introduce an additional arc, okay? From T to S, an additional arc. Now, everybody's B will be 0. Everybody, okay? So these guys also, my B's are 0. Every B is 0. I'm adding a new arc, okay? This new arc's cost is -1 and upper bound is infinity. Okay? All right. Then the cost of everybody else is 0. So everybody else's cost is 0. Upper bounds as given. Now think about this new network. If I solve MCNFP over this new network, I will minimize Cij, Xij. There is only 1 minus 1. Everybody else is 0. So in an optimal solution, the optimization will try to make sure that this -1 is multiplied with the largest x possible. Yeah. If I do minimizing Cij, Xij, and Xij is the amount I'm sending over the link. Yeah. It will try to make sure that the -1 is multiplied with an x as large as possible. What is my constraint subject to? Well, Xij minus Xji equals 0 over all I. So, okay, sending nothing is feasible with objective function value 0. And my xij's, by the way, should be between their bounds. Of course, sending 0, okay, feasible. Sending 1 unit, then if one enters to T, one should leave T, because flow balance says anything entering to 2 should leave 2, and it has to go back. So if one enters, one should also leave. That's the flow balance is actually sending 1 unit and making a cycle maybe, or I don't know, a couple connected, right? But then if I only send 1 unit, my objective function will be -1. If I can send 2, my objective function will be -2. So the optimization will try to send as large value over this x. This is a new one, so let me write it in an open form. So the optimization will try to maximize x61, because that's the only one with a -1 in the objective function, right? In order to increase x61, I do have flow balance, right? Anything coming into 1 should leave. Anything getting out from 8 should enter. So my flow balance will actually satisfy that I'm sending the largest possible value from S to T. It's flow balance together with my objective function optimization. Okay? Any questions? Is this clear? This was a little bit challenging, but with the inclusion of one link and a trickier cost parameter, we just converted the maximum flow problem to an MCNFP. Any questions? Okay. Then let's look at this MCNFP closely.
I had
Oh, okay. Okay, Dennis. It's so silent and all of a sudden a question yeah, what is the question? Do we write a bound for each arc? Where are the capacities of the arcs? Yeah. In here, the arc capacities are the original arc capacities, whatever they are. And the costs will be 0. So that when I solve this, I'll be sending the max flow.
So, Hocam, I didn't understand. Do we write inequality for each arc?
Of course.
Okay.
Now, when you start, actually, this is the time that you should start using those solvers. That's why you're going to have solver practices and everything in the near future. When you write the solvers, there are easier ways for you to write these. Okay, in the loops and everything. But yeah, we have a flow balance constraint for each node, and we have an upper bound constraint for each arc. Exactly. Any other questions? Okay, then let's look at this MCNFP closely, because as I was saying, we're going to drive an algorithm for this. Well, I'm going to teach you an algorithm, not drive. Well, yeah. So, as always, of course, we need to go to our matrix notation, yeah? Then, this is the format in our matrix notation. We're minimizing Cx. Of course, C is the vector, so it's supposed to be C transpose X. And subject to our Ax equals to B, and our X should be between the bounds. This is the structure. Now, why this problem is important, why is it unimodular, and everything is hidden in this A, because A is very specific. Let's see why. It is called node arc incidence matrix, because this A is actually the flow balance constraints, right? So for each node, we write anything in and out equals to the whatever the BI there is +1, -1, the demand, supply, 0, whatever. So this is actually for each node, this A matrix is actually like I have enough rows, as many rows as my number of nodes. And my arcs are actually in the columns in the same matrix. You're going to see why in a minute. So this matrix is called node arc incidence matrix. Okay. Each row corresponds to a node, and each column corresponds to an arc. Okay. And this is the structure. There is only, in each column, there are only two non-zero entries. There's a +1 where the arc is living, so the tail, and a -1 in the head of the arc. This is the structure of matrix A, actually. So if this is my arc, okay, so my tail will have a +1 and my head will have a -1 in the node arc incidence matrix. In this, when you write this flow balance constraints, that's what you will be seeing. Let's do it in here. Okay, this node arc incidence matrix. So let's see, this is 1, 2, 3, 4. Okay, these are directed. So my arcs are like this. I have an arc from 1 to 2, 1 to 4, 2 to 3, 2 to 4, 4 to 2, 4 to 3. So we have 1, 2, 3, 4, 5, 6 arcs, and we have 4 nodes. So our A will have 4 rows and 6 columns. Okay, each row corresponds to a node, and each arc corresponds to a column. Okay, I told you this is the structure, right? So that means for the column corresponding to 1, 2, the head will get a -1 and the tail will get a +1. The head is 2 in the arc 1, 2. So 2 gets a -1 and 1, which is the tail, will get a +1. As you see, arc 1, 2 from 1 to 2. Arc 1, 4 from 1 to 4. 2, 3 from 2 to 3. From 2 to 4. From 4 to 2 and from 4 to 3. So from gets a +1 and 2 gets a -1. As in the supply demand, from plus to is actually the absorbing side, which gets a -1. This is how we actually form our node arc incidence matrix. Given a network, okay, you can immediately write the node arc incidence matrix. Or given a node arc incidence matrix, you can immediately construct the network. Let's look at here. From 1 to 2, so there is a 1 to 2. From 1 to 4, there is a 1 to 4. From 2 to 3, there is a 2 to 3. My handwriting is awful, I know. So there is a 2 to 3. Then there is a 2 to 4. What else? There is a 4 to 2, and there is a 4 to 3. This is how it looks like. I draw it differently so that I didn't look at this picture. I just look at the matrix and write the network from the matrix. Is it clear? Node arc incidence matrix is a special A matrix, and this A matrix, given a network, you can immediately construct the A matrix. From node, from 2, from gets the +1, 2 gets the -1. Okay? So here, for example, this example was given this, construct the network. Let's see. From 1 to 4, there is a from 1. Let me switch colors. So there's a from 1 to 4. And the second arc is actually from 2 to 1. From 2 to 1. Third one from 2 to 3. From 2 to 3. Fourth one from 3 to 1. Like this. This one from 3 to 4. And from 4 to 2. Yeah? You can, given this, you can write this, and given this, you can write this. Okay? Given a graph, you can write the node arc incidence matrix. Given a node arc incidence matrix, you can write the graph. Be careful. Always remember, I to J, I gets a 1, J gets a minus. Supply gets a plus from 2. Okay? Now we will be seeing a specialized simplex that works on network simplex, that works on networks, on MCNFP. But before going to that, I have to open a parenthesis in our regular simplex and tell you something, what it is. Now, remember, when we solve simplex, we didn't have these. We solved simplex for mean C transpose X. Oh, my handwriting is awful. So we solve simplex with minimizing C transpose X subject to AX equals to B and X non-negative. This is where we worked up until today, right? This is normal simplex. Now, there is an upper bounded simplex version of it, which is a tiny change, a little modification, and the algorithm will work when you include these bounds. Okay. Now, in the regular simplex, we were since the rank of our matrix is M, we were looking at M linearly independent columns. Yeah, that was giving us our B, and the remaining N minus M variables, we set these guys to 0. Yeah, because we were trying to solve for the rest. Now, the motivation there, setting them to 0, was actually setting them to a specific value so that the remaining invertible matrix, B inverse, will give me the values of the other M, right? Now, instead of setting them to 0, we could set them to some other value too. 0 is their lower bound because everybody has to be greater than or equal to 0, right? Well, the upper bounded simplex, the only difference is this time, the simplex algorithm allows you to set them to their upper bounds too. Not just 0, but whatever the upper bound is, I can also assign them to their upper bounds. But then I have to be very careful in entering leaving ratio test thinking, because now, whenever we're entering a variable, we were always thinking that I want to increase the value of this guy. And the ratio test was actually based on the fact that I'm going to increase the value of the entering variable. But if I start assigning upper bounds, I cannot increase it anymore, right? So in that case, I have to think that this variable, I fixed it to upper bound, but apparently simplex doesn't like it like that. It's not optimal. If I decrease the value, sending it at the upper bound was not a good idea. So optimization wants to decrease its value. All right, let me decrease its value. Then I will be decreasing its value. And I have to consider it like that in the ratio test too. That's the only challenge you have to be thinking about. Other than that, machinery is the same. So the upper bounded simplex set N minus 1 non-basic variables to either 0 or to their upper bounds and solve for the remaining. The solution will again be unique because my B is invertible, right? The B inverse exists, so my basic variables will again be B inverse B. But I have to be careful because my non-basics are not always 0, right? So I assign some of them to their upper bounds. I have to be careful. XB is no longer B inverse B. It is also have to be thinking about the values which are in their upper bounds. We will not solve standard simplex with upper bounded variables, okay? Because you can check from the book, you can get yourself additional questions. But what we will be doing is we will actually utilize the idea of upper bounded simplex in the network simplex algorithm. Any questions up until here? Okay. I think I want to stop here right now because this network simplex is a completely new topic. I want you to absorb this network idea and converting to MCNFP, this node arc incidence matrix, and then Thursday is the holiday. Every day is a holiday, but whatever. Thursday, we don't have any class. next Monday, we have our quiz on sensitivity analysis. And the Thursday after next Monday, which is, I don't know what day it will be, we will be having the remaining of the network method. So in the second Thursday following this one, I will be teaching at 8:40 the network simplex algorithm. Any questions? But I'll stop here right now. Any questions? You mean the upper bounded simplex, Deniz? Is this a new question? Okay. All right. Let me repeat the upper bounded simplex. Remember, in the standard simplex, all we did was we selected n minus m non-basic variables, and we set them to 0. And then we solved for the remaining basic variables. In the upper bounded simplex, you could actually, the upper bounded simplex allows you to set those non-basic variables, not just the lower bounds, but upper bounds also. So some variables will be 0, some non-basic variables. Some non-basic variables will be at their upper bounds, whatever that upper bound is. Okay? All you have to do is you have to be very careful, of course, because now in assigning the values and everything, you have to keep in mind that your non-basic variables are either 0 or at their upper bounds. So you have to update the equations appropriately. Not just delete those variables because they're 0, but make sure that you're actually representing them being at their upper bounds. That's all I said. But I told you we will not solve upper bounded simplex in the simplex table, but we will utilize that idea in the network simplex that I'll be teaching not this one, but the next Thursday. Okay?